So far we've looked at data where the outcome of interest is continuous or scale, and now we're going to look at techniques when the outcome is categorical. Often this will be nominal data, but their techniques will work for some ordinal data too, depending on what it looks like. So I thought we'd just take a quick look at some examples of count data, which we would call discrete, because it can get treated in all sorts of ways depending on what it looks like. So imagine we were doing a clothing survey, and we were asking people about the number of t-shirts they own. These might be fairly high counts, and perhaps when we plot them they look fairly normal. And so in this case we would use the same techniques that we use for continuous data, like t-test, analysis of variance, etc. Imagine then that we ask people about the number of genes they owned. Now maybe these counts are a little bit less, maybe they're not looking quite so normal, and so perhaps we wouldn't use the parametric techniques, but instead we would use non-parametric techniques like maybe Mann-Whitney-Yu, Kruskal-Wallis, and we don't make assumptions about the shape of the distribution. Finally, imagine we ask people about the number of waterproof jackets they own. Now maybe this is looking very different again, in that most people say 0 or 1, and then you've got a few people saying some higher numbers. In this case, what happens is that we often want to group all those higher numbers together because there's not enough of them to look at separately. And so we might put these into categories of 0, 1 and more than 1, and essentially treat the data like it is just categorical data. And we would use similar techniques that we use for categorical data, like using a bar chart. And we could put the numbers into a table. So this would be called a cross-tabulation, a two-way table, or a contingency table. If we were interested in testing, is there any association between genders and jacket ownership, then we might use a chi-square test of association, where the null hypothesis is that there is no difference in the number of jackets owned between the genders, or there is no association between gender and jacket ownership. If the outcome variable actually only has 2 levels, then it's a special case and we call it binary. Examples might be if the outcome of interest we code as a yes or a no, sick, healthy, survived, died. It's very common in health data, and the results are nearly always reported in terms of odds ratios. The analysis that you see in papers might be called crude, or they might be called adjusted. So let's take a quick look at those before we delve into some of the details. So a crude or unadjusted analysis is the type of stuff that we've seen so far, where we just look at 2 variables at a time. So the examples I've taken from the textbook back in chapter 5, the outcome might be immunised or not immunised based on whether they received a call or didn't, or developed a disease, yes or no, based on whether or not they were exposed to pesticides. So this can be called univariate analysis because there's one exposure variable. Confusingly, it can also be called a bivariate analysis because it's looking at 2 variables together, the exposure and the outcome. I don't think I've ever seen a bivariate analysis refer to 2 exposure variables. So we've got the inconsistent terminology there. When we look at an adjusted analysis, it means that a more complicated analysis has been done taking account of other variables. It might also be called a multivariate analysis because they've got lots of variables in it, and it's similar to multiple regression except that the outcome is not continuous. So in this case, in this table that I've given just as an example, they've put in crude odds ratios and also adjusted odds ratios, so that you can see how the odds of having, in this case, multi-drug resistant TB, based on not just whether or not you had that previous treatment, I think that's what they were looking at, but also adjusted for age and sex and residence. So if we have a binary outcome and we want to adjust for other variables, the most common technique to use is logistic regression. And logistic regression in its simplest form, with no adjusting, is essentially equivalent to a chi-squared test. So I thought we'd take a quick look at that and revise the chi-squared test. So this was an example we've seen before, looking at the risk of hepatocellular carcinoma based on whether or not you are a coffee drinker. It was a case control study, so obviously the outcome happened first and then they tracked backwards to look at coffee drinking or caffeine consumption. They call it a univariate analysis, and that's equivalent to a chi-squared test. And then the multivariate analysis has adjusted for age, gender, smoking, alcohol, tea, and physical activity. And we can see that the odds are reported in, the results are reported in terms of odds ratios. And if we look over at the table, we can see that the odds of getting the hepatocellular carcinoma are actually less if you're a coffee drinker. And so there's an interesting body of research talking about why and how coffee might potentially have a protective effect for this particular case. Now, the chi-square test is quite a handy little test. It's one of the few tests that we can do without access to the raw data. With just knowing the counts, which we can get out of most tables, we can actually run the test ourselves if we want to. So as revision, I've copied and pasted the numbers into a table in OpenEpi. And we can quickly run the test to have a look at the outcome. The assumptions for the chi-square test are that the two variables are measured at an ordinal or nominal level, so it should be categorical data. Your two variables, and I think I'm missing an S there, should consist of two or more categorical independent groups. So again, that independence of observations assumption. And the test may be invalid if any cells have an expected cell count of less than 5. Now, this is not the observed cell count, it's the expected cell count that we would expect under the null hypothesis that the two groups have got the same proportions. And so we can't tell that actually until we calculate those expected values and run the test. So here we have the output from OpenEpi. The p-value, we're just looking at the two-tailed tests, is 0.068, so it's not quite significant. And there's a little sentence at the bottom saying that it has checked all your expected values and it's okay to use it. So you don't really need to check this yourself, although you can, but most software will do that for you and give you a little message if it's possible that your test is not valid. If you scroll down your OpenEpi output, you'll see the odds ratios. So the odds ratio of having the carcinoma if you're a coffee drinker is 0.0595. So maybe I should get my pointer out. So that's up here, and it's quite, this is what you would get if you did the test by hand, this value here, and then this is an adjustment made. And you can see that that's pretty much the same as what they reported in the paper, and then we have our confidence interval. And you'll notice that the confidence interval just covers 1 because it's not quite significant. We can run the same analysis in SPSS. You can do it without the raw data, although it's a little bit tricky. I think what I did was fake the raw data in this case to demonstrate it. There's lots of options, but what we're going to concentrate on is just looking at the sorry, I've lost my pointer. If we open up the crosstabs dialog, put in our exposure and outcome, and then the statistics, we can get out the chi-squared test and the risk, which will actually contain our odds statement. Put that down, get out of the way. It might be handy if that was actually labelled odds ratios, but it's not. So in SPSS, we'll get similar output, formatted a little bit differently. Down the bottom you can see that no cells have an expected count less than 5, so the test is probably valid. We get our cross-tabulation or contingency table, and then we get our p-value. And that's the asymptotic significance two-sided down in that bottom table. We can also run exactly the same analysis using logistic regression. Now, if you're wondering why can't we just use linear regression, It's because the outcome is not continuous, it's a yes or a no. So essentially what the analysis does is it models the probability of the outcome rather than the outcome itself. And probability, as we know, can only go between 0 and 1. So essentially what it's doing is it's taking that linear regression line and it's squishing it in between 0 and 1, and it gives us what we call the logistic regression curve. So it's still a regression technique, it's just a little bit more fiddly. So if you want to know the maths, this is what it looks like. A linear model is y is equal to the intercept plus the slope times whichever exposure variable we're interested in. And then the logistic model does all this very clever maths to basically take this straight line and squish it in between 0 and 1. Now this is not accessible, this is just for the people who have the math background and are interested in it. But it is still a regression technique, and that's why it's called logistic regression, because it's in the same great big family. So I like to think of the logit name coming from log it, where it is the probability of x divided by 1 minus the probability of x, which perhaps you can recognize as being an odd statement. And you might be wondering, why on earth would we want to do something so complicated? Because this logit is looking very messy. So it is looking messy on that side, but if you look at the right hand side of the equation where we have the beta 0 plus beta 1x, all of a sudden that's looking really simple. And it's looking like an equation where we can just keep adding more variables in like we did with the multiple regression. And this is why we can control statistically for other variables, because we're essentially just adding them into that equation. And I've put the link there for that webpage if you want to read a little bit more about the details for logistic regression. If you look at some of the menu items on SPSS, you'll see there's all sorts of types of regression. We're not covering all of those. We're just looking at binary logistic regression because it is one of the most common techniques used in health data. There are a lot of options. We're going to keep it simple. Usually we'll just be ticking the CI for XB, and that means the confidence interval for exponential of beta, which is the parameter in the equation. And this will essentially give us the odds ratios out. So you can look out for that XB in the tables, and that's our odds ratios. So if we have a look at this analysis, and maybe I will just get my pointer out again. So you can see here that we still have the beta in the first column, and this is actually a little bit difficult to interpret for logistic regression. I wouldn't recommend looking at this. Usually what we want to do is just look for this exponential beta, because this is our odds ratios, and you can see we've got the confidence interval. So this has come out the same as with the chi-square test, and it matches what they have in the paper, about 0.59 with a confidence interval from 0.34 to 1.04. So that's exactly the same as what they have in the paper. And you need to remember, of course, with odds ratios, it is a ratio, so it's comparing the odds of that outcome. In this case, the outcome is the hepatocellular carcinoma compared with another group. So it's always about comparisons. So for every one person with a hepatocellular carcinoma who didn't drink coffee, there were only 0.59 people who had the outcome who did drink coffee. So they've got a reduced odds of the outcome. So essentially it's saying that coffee is having a protective effect. So what I would hope that you can do is understand this last bit, the odds ratios and that 95% confidence interval. And as we saw, it's not quite significant. The p-value was about 0.06, 0.07, and the 95% confidence interval will match up with that p-value, and it's just crossing 1. And 1 would be the line of no difference between the groups. So I might pause the recording there, and then we'll pick up in the next video with how we might present the results.